Good morning, everybody. Welcome to episode 44 of our MakerBot Chats. My name is Felipe. As always, it's great to see you guys here. And yeah, let's get into it. We have an interesting one today. I actually just ran a new, fresh batch of BASF ultrafuse prints. Through the processing, the sintering process, I suppose. And I have a few things that I wanted to share, just generally speaking, on best practices, some of the issues that I've seen, some of the considerations that you might want to have when using BASF, from different scales of parts, different textures, kind of like the general good practices that I've seen and challenges that I've seen with the material itself, right? I'll switch over to my camera here, which right now has a few different, let me bring these guys into a better location, but a few different sample parts that I've, as I said, just received or gotten back from our sintering facility. Not our, but the one that actually Matter Hackers uses. Matter Hackers is a large filament distributor. They also sell the processing tickets for BASF, and yeah, I've got a fresh batch of these items. They all together, actually I'm missing this one. So this is the batch that I sent, which actually, I think illustrates one of the first points here. Essentially, how many parts and how big of a batch can you send out to be processed? And the answer is there's no real limit in the number of parts, right? You can send out as many as you want. Let me see if I can change the glare here a little bit. Let's bring down this curtain. Oh, a little bit better, maybe. Okay. Maybe more. But anyways, so there's no real limit on the number of parts that you're able to process with them, right? It's the limit is on the weight. So every single purchasing ticket is going to be about, or cover you for 1 kilogram of material. This was close to 1 kilogram, so about 950 grams. Pretty spot on. I actually planned for it, right? I try to collect as many parts as I have or as I'm able to in order to maximize the use that I get out of the processing ticket. So it was 6 parts that got sent out. As you can see, I was testing different things. They all tend to be reasonably flat, reasonably shallow. I was testing different, geometries, kind of. You've probably seen me use this part before. I have processed it a number of times. I wanted to see, how big of a part I could get. As you guys might be aware, there's a limit on the part size that you can sinter. The limit now stands at about 100 millimeters cubed. So about 4 inches cubed all in all. The closer that you get to that edge or to that limit, the easier it is for you to get issues, warping, curling, misprints, and fails in the processing overall, right? So yeah, mostly flat parts, mostly shallow parts, testing different textures, testing kind of like the possibilities on, gears, tolerances, this little sprocket as well, kind of like a little bit of a more complex part, I would say. I will use also my macro lens in a second so that you guys can see. So now the macro lens is on, so you guys can see kind of like the in detail shot of how do these parts look right up close. And I'm really happy with the quality of them, right? It's not perfect, I have to say that, right? It's not BASF. It's a great, impressive material, right? The quality is the fact that it's 100% metallic. That's amazing. However, it is definitely a tricky material to print and then post-process. The good thing about it is that now that I have them sintered, now that these parts are solid stainless steel, there's a lot of things that I could potentially do to them in order to finish them up, right? I could buff them, I could sand them, I could solder on them, I could grind them. Any type of process that I would normally apply to a metal part is something that I now can do with these 6 parts, right? And the other thing that I wanted to show, if I switch over here, and I want to bring also a camera view. But the other thing that I want to show is kind of like the differences that there are in, here we go. The difference that there are in the shrinkage rate for these parts, right? So how big a change, so if I fade here, I've got my Rhino screen going on, and I've got all of these parts, right, laid out here, and I want to show you guys how big of a change do I see between the model part and the actual part that I got back from BASF. Generally speaking, you want to scale these parts up about 20% in X and Y and 26% in Z. That is because there's a larger shrinkage rate in Z than there is in X and Y. So I'll take it a step back. You know, for those of you guys who might not be familiar with printing metal filaments, right? This particular filament needs 3 steps, right? First step is the printing stage. Second is the sintering stage, and then the third one is the actual usage of your metallic part. During here we go. During the printing stage, you will want to accommodate for a shrinkage, a noticeable shrinkage that will happen when you process and sinter your parts. That shrinkage tends to be, as I was saying before, 20% in each of the axes except for the Z-axis. Why? That's because the weight of the part itself, right, is going to further compress the part downwards and in turn create an uneven shrinkage in the vertical axis, right? So you will want to scale up your parts about 20% in X, 20% in Y. That'll cover you for the planar shrinkage, and 26% in Z. Again, it's an uneven shrinkage, and unfortunately each part will have different issues, as you will see in a second. But overall, that's a good rule of thumb. And why do I say that's a good rule of thumb? Because if I move back here to my Rhino window, right, you can see, for example, this range, which is, I printed it twice, but this is the actual scale that I used. So this range, supposed to be, you know, 110, short of 110 millimeters across, and you know, having a 15 millimeter wrench key here, which was kind of my main feature. I gave myself a little bit of a buffer here, so I wanted it to be 15.6 millimeters just to make sure that I had enough clearance to actually use the wrench. Let me move it a little bit here, and the overall width 25.98, so close to 26 millimeters. Now let's go ahead and measure this guy out. So I of course have my very handy, switching over views again, caliper. There we go. It's been kind of acting weird on me for some reason. I feel like the battery's either it's dying or it's about to die, but anyways, let's just measure this first part out to begin with. So we've got 26.35, and let's have them both at the same time here. If I can make this just a little bit larger, I want you guys to be able to experiment and experience the whole thing at the same time. So we've got a nominal spec of 25.98 here on Rhino, right? And an actual part that's 26.23, right? So really close, about 200 microns of that initial spec here in the main sort of boxing element of the part. If I take the main axis here, should be 110 according to Rhino. Let's measure it out here on the part. Whoa, 110 flat. I mean, it's about 600 microns. So, well, 109. Whoa, 109.9, right? You guys can see that. Let me see if you guys can actually see. So really close to it. Here's my measurement, right? Really close. It's actually, I'm a little bit surprised about how close these tolerances are and how close this sort of ballpark measurement is of the 20% rule. So again, all that I did here for it to print successfully was scaling the parts in MakerBot Print 20% in X, 20% in Y, and 26% in Z. And you know, unsurprisingly, I guess, because kind of like that's the the expected outcome. I got parts that actually match those dimensions. And overall, you know, taking a little bit of time to review this particular part, let me switch back to my main camera view here, right? So you see there's a few things happening here. So the part, let's use the macro lens for a second. I'm happy with the resolution of the part. I'm happy with the roofs of the part. Overall, it was processed successfully. Even this logo, which I wasn't sure if it was going to come out, you know, properly or not from the machine. It's kind of rather crisp, and you can see how the logo, even though the part is printed solid, the logo itself defaults to sort of a two-wall, you know, print, because of the fact that it's a little bit too thin for the slicer to cover the space inside of those letters. But even though it's using a single wall for these letters, right? I'll bring it even more close. Yeah, it actually came out really crisp. The M itself is actually completely filled up. The rest of the logo, you know, the MakerBot is it's not. It's just using the external walls of the logo to draw it out. But still, I would say I would qualify that as a success overall. A few little dents here and there on the roof. These actually, and it goes back to, you know, what I was trying to print. If I fade here, as you can see, my original part actually had this 10 millimeter text here and 15 millimeter text here. The idea being that I wanted to engrave the actual values of those two wrenches, right, to make sure that they were easier to sort of visualize while using the tool. But as you can see, that was a little bit too close and too small, so the slicer didn't even bother. I mean, it did try. As you can see it here in the 10, I think it's a little bit a better example. So it is kind of trying, but it didn't really succeed on printing such a small scale element, right? So I would say that features that are smaller than 5 millimeters and particularly thin, just like text would be, are going to be a challenge. However, anything that's above that, like this lettering itself, the method lettering, is going to be, let's see, I'm assuming that about 5 millimeters. Yeah, 5.9, so close to 6 millimeters here on the logo itself. That's the height of the logo, and it printed out without much of an issue. The big thing to consider is that it's not going to be entirely filled up with material. So yeah, just an additional thing for you guys to keep in mind as you're attempting these type of geometries, embossing them with text or similar fine detail elements, right? Let's move on to the next part that I've got here in Rhino, and let's do the sprocket real quick. So for this sprocket, my main dimension, and I have it here, removing the macro filter or the macro view, right? It's a fairly straightforward part, a few teeth. I think it's about 17 or 19 teeth, I'm not sure. And then I had different elements here, concentric diameters, a few location keyholes, and then just weight reduction elements here to the sides. Now, these radius was supposed to be 34.5, almost 30.47. Let's measure it out. Oop. As I said, I'm having some issues with my caliper. But here we go. The actual dimension, 33.2. Let's do it once more. Different angle. 34.24 here on my main diameter. So pretty close, pretty darn close to that final dimension. 33.4, 33.4, 33.6. Again, this shows kind of like that uneven shrinkage, and I can actually see it a little bit. I don't know if, like, let's put it against the grid here. If you see it against this, and I'll make sure that it's actually visible here on the camera, but if you see it against these squares, there's a little bit of an uneven deformation here, and I think it has to do with how these elements, how these keyholes are affecting and distorting the shape itself because of the very thin element and very thin bridge that occurred here, right? So that very thin element is actually pulling apart the part and distorting my main circle. You can see how there's a little bit of a dent here. I think it's mainly driven by that change in diameter. You can also see it here, right? There's a little bit of a deformation. I'll bring in my macro lens again and switch over to this view, right here. This is much easier to see. So you guys can see, let me bring my handy pen, but you guys can see how anywhere where I get too close, here we go, to these key elements, there's an uneven shrinkage happening, right? You can see it here, you can see it here. Here it's not occurring as much, and I think it has to do a lot with the fact that it wasn't just this very thin, narrow bridge of material, right, that you guys can see here, but rather the keyhole was located against a beefier section of the part, right? So this section actually was able to counteract any uneven deformation that was happening here on the part, but that didn't really happen here, right? So you can see how there's like it's almost like a dent in the part right there, and the same thing is happening right here, where yeah, it's just pulling unevenly with the material. And as we've said in the past, the thinner the feature, the more uneven the feature, the more likely that this is going to, oh, let me center that out, the more likely that this is going to happen to you, right? So one thing to keep in mind, and I think that that's a good learning for next iterations here, would be to place these keyholes against beefier elements, right? Or to give myself a larger margin here, because I think that this should be about 1 millimeter across, maybe 2 millimeters. Let's measure that out real quick. So up. Yeah, just 1 millimeter, a little bit over 1 millimeter here. So that's not enough material to guarantee kind of like a proper shrinkage of the part. It's just going to have or to cause you a lot of issues. And again, if this is something that you can play with some of the design constraints, just by had I aligned these elements, these keyholes against the beefier components, just like I did here, accidentally or not, but like I did here, I would have guaranteed a much more even circle overall and less of a deformation like what we're seeing particularly here, right? Where you see how the circle is completely, it's not completely circular, it's just a minor dent. It's not a lot, right? It all depends on how tight your tolerances are going to be. I'm removing the macro lens here for a second, but it's still there. So something to keep in mind with this particular part. Now, next part over, and I'm going to start jumping into some of your guys' questions in the background as well. It's going to be this 3-point attachment, right? So I just basically created this part. Let me zoom it in Rhino, bring it back from Rhino. Here we go. Sorry, just a second. Centering this part out in Rhino so that you guys can see and follow along. Here we go. So you can see the Rhino part, you can see the actual printed part right here in my hand, and the fact that, yeah, I think overall the details are captured fairly successfully. However, there's, if I bring in my macro lens again here, this very smooth tapered sort of surface is going to create issues with my layer attachment, especially, and I think this all happened after the fact during the sintering process, because of the fact that some of these layers, it's kind of like a similar issue to what I was talking about before with the keyholes in the sprocket that I just showed you guys. But these very fine layers start to delaminate. You can see the shadow almost clearly visible there. Like it looks like a crack, but what's happening here is that some of the layers are just simply unable to attach properly to the previous layer. And I think that that's mostly due to the fact that these layers end up in a very, very, very thin edge, right, that has nowhere to attach to. So this very organic shape, if you look at the cross-section like there, you can see how there's this very nice smooth curve happening, but that smooth curve in turn causes issues, as you guys can see here in the delamination. And it's just on those elements, right? It's right on the edge where the layer starts, where it doesn't really have a place to attach to, where you will see those delamination happening. Overall, depending on what my application was for this part, I would say it's something definitely that I could be using it for affixing something against a wall. In this case, my aim was just to create this kind of vertical anchor for a pipe. So 3-point attachment and a centerpiece with location holes spread it throughout. And yeah, overall a good result, but again, something to keep in mind. These smoother edges are going to be kind of challenging. Let's look at the actual dimensions so you guys can see there in the background. 10.4 is supposed to be my radius. If I measure it out here, my part, a little bit more. So 10.4 should equate to 20.6. 20. Is this the correct part? Let me just make sure that I'm getting you guys a. Here we go. It's actually this one, because I was actually zooming into the unscaled part. So once more, 12 millimeters, that should equate to about 24 millimeters here. If I measure it out, we are 29. That's odd. It's much bigger. Maybe I misscaled this part out. But overall, you know, much better resolution on the circle. Again, it's a smoother part. It's a more even part. So the circular features are going to be better respected, right? Even if I have these keyholes, they are not affecting that circle in any major ways, because of the fact that, as I said before, let me fade in here to the main camera view. Again, the more even the part, the more consistency you have on the part, right? These holes, definitely will affect how your part behaves. But because of the fact that they are evenly and constantly distributed along the part, then there's not a major deficiency seen on the part. And that's also true for these other three elements, right? The actual attachment points. So overall, I would say a good success. The learning here is more around how do you actually keep in mind that these smooth surfaces, these smooth transitions are going to have sort of certain or create certain challenges for you during the sintering process. I'll stay here to in the Rhino window so that I can have like everything at once, and I'll start to cover some of your guys' questions right here. So, can you give us a rough idea of how much the sintering process costs? Okay, yeah, sure. It's not a rough idea. The process itself, it's $50 per kilogram. That's on the regular ticket. And if you want it expedited, it's about $80. I had them expedited. I would say that I haven't seen really a massive difference in time change between having it expedited versus having the regular process. The really big thing to keep in mind is the timing, right? So you really want to make sure that these parts make it on time, in time of the cutoff. And the cutoff happens twice per month on a Tuesday. So you want to send your parts no later than the Friday before, just to make sure that they get there on time and are processed the week of. If they get there on time, and if they are processed on that week, that means that they'll be processed on a Tuesday. If you do the expedited shipment, you will probably get them on Thursday, maybe Wednesday, but I've always seen it be like kind of like a 2-day delay. So you get them in on Monday, you get the expedited ticket, and they get back to you on Thursday. If you have the regular processing ticket, you're looking at probably Friday, maybe Saturday for the parts to come back. So it's essentially 1 week processing time overall, right? And that's kind of like my best, my impression of the service overall. Can you electropolish stainless steel following sintering? What's the roughness of the surface? Right. It depends. The surface finish roughness depends a lot in your part, right? As I was saying before, and let me go back here to my macro view, putting the macro lens on, right? It depends a lot on what type of walls and features you're talking about. If it's, roofs, floors, these vertical walls, the finish itself is pretty smooth. It's kind of nice, and definitely you could electropolish it. However, as going back to this other example, the more organic shapes, the more sort of smooth. It's kind of ironic, right? The smoother transitions will have a higher degree of bumpiness and roughness to them. That's at least in my experience, right? Something that's very vertical. Let me bring another part here. This is an old part that I had already processed, but something that's very flat, vertical, straightforward. It's going to come out with an amazing surface finish, right? Even if it's kind of blobby, But as long as the blobs are not super, you know, uneven, then you can still have, and this of course I polished myself. I just polished it with sandpaper. There's nothing big here happening. The inside surface is the actual natural surface without any polishing happening. But yeah, as I said before, the more even your part, the more likely that you will get a very smooth surface finish. Removing the macro lens again. What is the printing requirements for BASF? Right, so you can print BASF with any one of the method printers. That's the Method X, the Method Carbon Fiber Edition, any one of them. You just need a lapse extruder, right? And speaking about technical requirements, BASF will print itself. The extrusion temperature needs to be 260 degrees. And then the chamber temperature is, I think, 60 degrees Celsius, right? So the heated chamber temperature is going to be 60 degrees. That keeps the material kind of at an even temperature and allows for a better print quality. What's the relative difference in shear strength between the metal and carbon fiber material? Okay, that's a really good question. And I would say that it's, definitely metal is going to be way stronger than carbon fiber for certain applications. The limiting factor here is that metal is definitely going to be way heavier parts. You're a little bit more constrained in terms of the shape of the parts, right? You cannot create very complex parts. And I think that we've used this in the past, right? Where we have like kind of this assembly of both metal elements and carbon fiber elements, depending on what you're trying to do. So for this particular gripper, I think that printing it all in metal, that's something that you could certainly do. All of these parts would probably fit in that 100 millimeter build envelope. However, you would end up with a part that's very heavy, kind of expensive, and I think that you wouldn't be getting the most out of each material. So for the high wear element like the gripper tip itself, yeah, 100% I would use the metal, the BASF. For the lighter elements that make up the assembly, I think that that's where carbon fiber really shines, because it's got the stiffness, it's got the lightweight, and the ease of use, and also the fact that you can print more complex parts overall because of the fact that you have access to soluble supports. Is it possible to use soluble supports with the UltraFuse 316L? Yeah, that's exactly what I was saying. No, it's not. BASF UltraFuse has to be printed either without supports or with breakaway supports from the same material, right? And that means even if you print it out with the breakaway supports, if those supports are sintered, they will be sintered into your part, right? It's going to be impossible, or well, I mean, you would need to grind them, and it's going to be really hard for you to remove them, because as much as the part would, the supports themselves actually become also metal because they are printed out in the same material. So it's tricky. You can definitely print supports with it. You cannot print soluble supports. And I would say overall, printing parts that don't require supports will guarantee, just in general, a better experience with the material. Do you need a special nozzle for metal 3D printing? No. All that you need is a lapse extruder. The lapse extruders comes with a replaceable nozzle. The only reason for that is that, if the nozzle wears out, if it clogs, if you're using kind of odd materials for your parts, maybe you sort of maybe you'll end up wearing the nozzle, or the nozzle can become clogged. So that's why we ship out the lapse extruder with multiple nozzles. But no, there's no particular unique nozzle that only covers metals. So yeah, definitely I would recommend keeping a dedicated extruder for metal 3D printing. It's just cleaner. I keep going to that same analogy. It's just like drill bits, right? When drilling in wood, you have your wood drills, your wood bits. Drilling on metal, you have your metal bits, you have your plastic bits. Doesn't really matter. It's important, it's cleaner, and it's going to give you overall a better experience. And with that, I think that we've covered all of the questions today. Thank you guys so much for joining. As always, you can reach us at hello@makerbot.com. My name is Felipe at makerbot.com as well, and of course social media, always an open channel for us to talk. At MakerBot, both in Instagram and Twitter. I'll try to make more of these. And by the way, next week, in 2 weeks' time, we'll be out on TCT Rapid in Chicago. So if you guys are coming over, make sure to come around and say hi. There's a bunch of us, well, not me, but there's a bunch of people in their team attending the show. So yeah, if you guys want to see the method in person and you're happening to attend Rapid, Looking forward to seeing you guys out there. And yeah, for now, that's it. Thank you guys so much for coming over, and I'll see you next time. Bye.